This is the next part on our study on transformations. In previous lessons, we looked at these kinds of transformations. So we looked at vertical translation or shifting, horizontal translation, shifting. Now remember, sometimes we use the word translation, sometimes we use the word shifting. We also talked about reflection. So we talked about reflection about the x-axis, and we talked about reflection about the y-axis. Now, if you go back to the lessons, you're going to notice that the shape of the graph, when we did these vertical and horizontal translations or the reflections, the shape of the graph did not change at all. So it was the same opening. It did not change. It didn't become narrower or wider. It stayed the same shape. Okay, now, what we're going to talk about here, though, in this lesson, is we're going to look at vertical stretching and vertical shrinking. We're going to look at horizontal stretching and horizontal shrinking. Okay? Now, when we do these, you will notice that the shape of the graph will change. So this vertical stretching, shrinking, horizontal stretching, shrinking does affect the shape of the graph. So does affect the shape of the graph. Okay, so the first thing we're going to do, though, is we're going to talk about that first arrow right here. We're going to look at vertical stretching and shrinking. So vertical stretching and shrinking. So that's going to be the first thing we're going to study. So vertical stretching and vertical shrinking. So what exactly do we mean by those words? Depending on the textbook, though, I just need to remind you, the word shrinking, some textbooks will use the word compression. All right, so the word compression, so keep that in mind. So they could say vertical stretch or vertically compressed, okay? All right, so when we talk about this, let's start with our parent function, f of x equal x squared. So remember, that's what the problem looks like for our parent function. Remember, we talked about parent functions in a previous lesson. So our parent function. And from this parent function, remember we did all the other stuff. So we shifted horizontally, vertically, we reflected, and so forth. Okay? So that's our parent function. We want to start with our parent function. All right, now what I want to do, though, is talk about this in terms of stretching it vertically and shrinking it vertically. So I want to talk about this in terms of stretching it vertically and shrinking or compressing it vertically. All right, now you're gonna. I gotta say this as we go on. The way it's going to look is this. So you will have a vertical stretch or shrink if you have this situation. So so you're going to have vertical stretch or vertical shrink if you have this. Y equals some constant times f of x. So whatever your function is, and you have a constant other than 1, okay, other than 1 here, then you're going to have a vertical stretch or a compression. Now I'm going to say this, though, for right now we're talking about C, where C is positive. Okay, so C is positive, because remember, if C is not positive, if C were negative, remember that would be a reflection. Okay, so we just want to talk about this in terms of C being positive for right now. Okay, all right, so let's look at our first example. All right, I want to look at, let's consider y equal, and let's say h of x. So let's say this is h of x, our function h of x. And let's say h of x is 2x squared. Okay? So we know what x squared looks like. So my function x squared looks like this, right? Looks like this. And in fact, when we plotted these points, we ended up with this. So when x was -4, Negative 4 squared is 16, right? So we got 16 here. And so that's this point right here, okay? So that's the point, negative 4, 16. So here's negative 4 right here, and then 16. And then if x is negative 3 times itself, remember, is 9. So negative 3, 9 is right here. Okay, so that's negative 3, 9. All right, and then so on. So negative 2, remember we got 4. Negative 1 squared was 1. 0 squared was 0. In fact, that was the vertex, right? And then 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. Okay, what I'm interested in, though, is this. What happens if I have, instead of f of x equal x squared, what happens if I have 2x squared? All right, let's look at this. So let's look at h of x. So where h of x, y equal, h of x is 2x squared. Let's see what happens there, okay? So if x is negative 4, so here's our x value. So if x is negative 4, now you got to look at what I'm doing here. If x is negative 4, where we see the variable x, I'm going to substitute negative 4, okay? So if x is negative 4, h of negative 4 would be what? Well, negative 4 squared is 16. 16 times 2 is 32, right? So that becomes 32, okay? I'll agree with that. Negative 3. Negative 3 squared is 9. 9 times 2 is 18, right? Negative 2. So let me go ahead and draw a line here. Negative 2. Negative 2 squared is 4. 4 times 2 is 8. I want you to notice something as we go through this, though. So this was x squared, right? And this, this is my function f of x, which is x squared. Y'all agree? I want you to notice something. This right here, isn't this right here? And we're going to go ahead and talk about it right here. So you see where I have h of x is 2x squared? You'll see that? Well, isn't x squared f of x? And so do y'all agree I can write this as h of x equals 2 times f of x? Because that's what x squared is f of x. So remember, f of x is y, right? So that's saying that h of x takes these y values and does what to it? Takes these y values of f and does what to it? Multiplies it by 2. So do y'all see that my y values are doubling? 16 times 2 is 32. That's what this says, right? Multiply by 2. So you multiply all these y values, because that's x squared. X squared is f of x. All these y values by 2. So do y'all see that that's what's happening? That this number c here, this coefficient, takes these y values and multiplies it by that number. So instead of saying, if x is negative 1, going through here and saying negative 1 times itself is 1, 1 times 2 is 2, all I have to do is take my y value and do what to it? Multiply by 2. All I've got to do is take this y value and do what to it? Multiply by 2. 0 times 2 is still 0. Take 1, multiply by 2, right? Take 4, multiply by 2. Take 9, multiply by 2. So remember, it's doubling. That's what this says. So this says I take my parent function, the y values, and I'm doubling those y values. So the x values stay the same. See, the x values stay the same. My y value for h of x doubles from the parent function. So I'm going to graph this now. Now, remember, I'm graphing this right here, right? So remember, when x is negative 4, what's the y value? 32. When x is negative 3, remember, I'm going to go ahead and do this. So this right here, so for h of x, my ordered pair would be negative 4, 32. My ordered pair here would be negative 3, 18, right? My ordered pair here would be negative 2, 8. My ordered pair here would be negative 1, 2, and so on. All right, so I'm going to go ahead and plot those points. All right, now, I'm going to plot the points in that same plane here. Now, obviously, I can't do negative 432 because it doesn't go, it only goes up to, what's that, 18? All right, so I'm not going to use that one, but I can do negative 318. So here's the point, negative 318 on h of x. Remember, right now I'm graphing h of x. All right, so negative 318. So 1, 2, 3, right here. 1, 2, 3, and then 18. So that is right here, right? Okay. And then the next one was negative 2, 8. So here's negative 2, 8 right here. All right. Now I drew this by hand, so it's not a very good shape right now. And then, because you're going to be doing this by hand yourself, so just do the best you can with drawing these parabolas. The next one was negative 1, 2. So negative 1, 2 is right here. Okay. And 0, 0 is the next one, right? 0, 0, right here. The next one was what? 1, 2. Then 2, 8. And 3, 18. And 4, 32. Okay? So I'm going to go ahead and plot those points. And so the green graph, I'm using a green color here. So the green graph will be h of x. All right, so watch what happens. So the next one was 2, 8, right? Is that correct? Yep, 2, 8. And the next one was 3, 18, which is here. So we should see what happens. So when I draw, now remember I'm drawing h of x. And remember h of x is 2x squared, which means 2 times my parent function. And so I get something that looks like this. All right, now, okay, this is what happens. Okay, just like that. Do the best you can with connecting them. Make it look like a parabola the best you can. I know you're doing this by hand, and you get something like this. So this green one here, this green graph, the green graph is h of x, which equals 2x squared. All right, now remember the blue graph is h squared. All right, so I want you to notice something, and I want you to notice something real quick. You may not be able to see this right now, but you see this distance right here, Okay, this distance right here, that's 1, right? That's 1. So I'm doubling that distance. So this distance is what? 2. This distance right here, when x was 2, that was 4, right? I'm doubling that distance. That distance is what? 8, correct? And so on. So that's what's happening. So you're doubling these distances. That's what this says. Okay? So if this was 3x squared, then it would be like this. It gets closer and closer, more narrower to the y-axis. All right, so do you see what happens? So the number in front of my parent function, affects the y value. All right, so the bigger the c becomes, 3, 4.7, 8, the more narrower it becomes. Okay? The more narrower it becomes. Now, here's what I want to do now. So that was 2x squared. Okay? I want to look at this though. Let's look at this. What if I had y equal k of x, which is 1/2 x squared. Okay, so y equals k of x, which is 1/2 x squared. Now, just like we did a while ago, so remember k of x is 1/2 x squared, right? Well, isn't x squared my parent function, f of x, right? So do y'all agree that k of x will become 1/2 f of x? So this says this, that whatever remember f of x is y here, same thing as y, your y value. Whatever my y value is, then k of x, the y value for k of x the y value for k of x is going to be half of that, right? So that means this. That means that 16 becomes what? What do you think? 8. You're taking half. 9 becomes 4.5. 4 becomes 2. Okay? So you're taking half of that y value for your parent function. All right, so let's do this the long way for first, and then we're going to come back to this. All right, so if x is negative 4, what's a negative 4 squared? Negative 4 squared is 16, right? What's half of 16? 8. So remember a while ago we said we were going to get 8? My y value was 8. I take half of that. So for this one, I doubled this and got 32. For this one, I'm going to take half of it. I'm going to get 8. So my y values, instead of getting bigger from your parent function, they're getting what? Smaller. Okay? So 9 becomes 9 halves, right? Because 9 times a half is 9 halves. I mean, if you check it, look what happens. Negative 3. What's negative 3 squared? 9. What's 9 times a half? 9 halves, right? Or 4.5. And then what I want to do now is, instead of taking these x values and substituting in here, I want us to use this idea. All right, so if my y value for my parent function is 4, then my y value for this function then will be what? 2. And then what's half of 1? 1 half. What's half of 0? Right here? 0. What's half of 1? 1 half. What's half of 4? 2. Because remember, what we're doing is we're taking this y value, that's this column here, multiplying by half. What's half of 9? 9 halves. And what's half of 16? 8. Okay? So, if I graph k of x now, remember this is k of x right here. So if I graph k of x in the same one, in the same plane, let's see what happens. Okay, I'm going to use red this time. So remember, the blue one was my parent function. And I know that remember, your coefficient of x squared is 1. This is bigger than 1, right? So if your coefficient is bigger than 1, then the graph's going to be above your parent function. See how it looks? What about for 1/2 x squared? All right, let's plus some points. So I have negative 4, 8, right? Negative 4, 8. Negative 4, 8. So I plot that point, I get this. Negative 4, 8 is here. Okay? Right here. The next one is negative 3, 4.5. Okay? Negative 3, 4.5. So that's about what? About right here. Okay? Right here. 4.5. All right. Right here. And then the next one is negative 2, 2. Okay, so negative 2, 2, which is right here. Then we have 0, 0. All right. Then we have 2, 2, right? 2, I'm sorry, 1, 1/2. I've got 1, 1/2. I forgot 1, negative 1, 1/2. So negative 1, 1/2 is here, right? All right, and then 0, 0. All right, then 1, 1/2. And then 2, 2. And then the next one was 3, 4.5. So that was 2, 2. 1, 1/2. 0, 0. Negative 1, 1/2. All right, and then the last one is 4, 4, 8. And so 4, 8 is right here. And so that graph is going to look like this. Okay? All right, so that's that graph. So here's the thing. If this was 1/3 x squared, 1/3, then what would be happening to these numbers here? They would become even smaller, because 16 divided by 3 is smaller than this, right? So my y values are even getting smaller and smaller. You agree? So the smaller c is, in terms of proper fractions, this is how it looks. Okay? So let's have a discussion about what we see here now. Okay, so here's what we need to take away from this. Okay, so I want us to take this away. So remember, first of all, we graphed h of x here. That's that green graph, h of x, which is 2x squared, and we talked about this. We said that this was the same thing as saying h of x was equal to 2 times f of x, because f of x was x squared. Then we looked at this. We looked at k of x, which we said was 1/2 x squared, right? And we also wrote this as k of x was 1/2 f of x. All right, now we're looking at c. So c right here. So c is 2 here that we did, and c here is 1/2. Okay, so listen carefully what I'm about to say. If c is greater than 1, all right, because remember, c is 1, that's your parent function. That was x squared. Remember, that was where we had 1x squared. So that's your parent function. But if c is greater than 1, like 2 or 3 or 7.5, whatever it may be, if c is greater than 1, then we say then the graph of y equals c times f of x, so y equals c times f of x, is the graph of y equal f of x, so f of x, but vertically stretched. Vertically stretched. All right, vertically stretched. All right, so if you look at this, so that's h of x. So here's my parent function. So what I did, according to that statement that I just wrote, according to the statement, I take my parent function, I take f of x, all right, and I'm going to stretch it vertically. So you're stretching this vertically, so you're taking f of x, the blue graph, and you're stretching it vertically by a factor of 2. All right, you're stretching it vertically by a factor of 2. All right, so it becomes narrower. So it's like taking a rubber band and stretching it. So you're stretching it towards the y-axis. All right, so you're taking a blue graph and you're stretching it. So when you stretch it, you get this green graph. Okay? All right, so listen carefully to this statement. All right, so I'm going to write this here. Okay, so to obtain h of x, which equals 2x squared, all right, we stretch vertically f of x, which equals x squared, by a factor of 2. All right, so we stretch by a factor of 2. So that, remember a while ago we wrote this as h of x is 2 times f of x. So 2 is a factor, so you multiply by a factor of 2. Okay? So whenever c is bigger than 1, you have a vertical stretch. So it makes the graph look narrower. Okay? So a vertical stretch, let me make this statement as well. A vertical stretch. A vertical stretch pushes the graph, So it pushes the graph of y equal f of x, so our parent function in this case, away from the x-axis. All right, so it's pushing it. Oh, see, this is the x-axis right here, right? So h of x takes f of x and pushes it away from the x-axis. So basically, you're going towards the y-axis with it. Okay. All right. So the larger c becomes, the more narrower it becomes. Okay, so it looks like it gets skinny and skinny and skinny. You see that? Okay? All right, now. Okay, so let's look at this one then. So we know what happens if c is greater than 1. So if c is greater than 1, then I take my parent function and I stretch it vertically by that factor. So it becomes, the larger c becomes, the more narrower my graph looks. All right, so if c was, let's say, 5, then it would look much more narrower. See that? That's important to see. Okay. Now, our other problem, though, was this. It was 1/2. Now, 1/2 is not greater than 1, right? 1/2 is what? Less than 1. Okay, so let's talk about this. So if c, now remember a while ago we said c was positive, so I'm going to go ahead and make this statement. So if c is less than 1 but still positive, so c is between 0 and 1, meaning a proper fraction, like 1/2, 1/2, 2/3, 3/4, things like that. So if c is between 0 and 1, so if c is less than 1 but still positive, what happens is I get this. So my parent function now looks bigger, right? All right, so it looks like I'm not stretching it anymore, but I'm making it go towards the x-axis or away from the y-axis. Okay. All right, so if c is less than 1 but still positive, the graph of y equal c times f of x is the graph of y equal f of x. Okay, so y equal f of x right here, f of x, but vertically shrunk. Vertically, so that's that shrinking. Vertically shrunk or compressed. Okay, so vertically shrunk or compressed. Now, what that means is this. So the red graph, to get the red graph, I take my parent function, the blue graph, and I pull it towards the x-axis. All right, so I'm pulling it towards the x-axis. I'm taking that blue graph, x squared, and I'm pulling it towards the x-axis. So if c is greater than 1, I take my parent function, pull it away from the x-axis. So I'm kind of stretching it. So I'm like pulling on a rubber band, pulling up on a rubber band. Then if c is between 0 and 1, so if c is less than 1, still positive, I'm pulling it towards the x-axis. So then you could have another one that looks like this. Okay, it could look like this. All right, where c here, if this is 1/2, then this has to be less than 1/2, right? So it becomes, looks like it becomes, I don't want to use that word, but fat. So this looks skinny, this looks fatter, right? Okay, so I'm going to make this statement. So I'm going to go ahead and do that here. So listen carefully. To obtain k of x, remember this is k of x. To obtain k of x, which equals 1/2 x squared. So I take my parent function, so we vertically compress or shrink, vertically compress or shrink f of x equal x squared by a factor of 1/2. So meaning that all of my y values on the blue graph, I am multiplying by 1/2 in this case. So this was, let's say this one here was 1/5. Then I'd multiply each of these y values by 1/5. All right, so before going to the next one, if your function is being multiplied by c, then you are dealing with a vertical stretch or vertical compression. It is a vertical stretch if c is what kind of number? Yes, c is positive, but it also has to be bigger than what? Bigger than 1. It is a vertical compression if c is still positive, but less than what? 1. Okay? And so if you draw your parent function and you have a vertical stretch, then it looks skinny. It's like you're pulling it towards the y-axis or away from the x-axis. Okay? If c is 1/2, 1/3, 2/5, then you're pulling your parent function towards the x-axis by that factor. Okay? All right, so I know it is not an easy concept to understand, the idea of stretching and vertical stretching or vertical shrinking. It's not an easy concept, but hopefully if you go back and you look at what's happening to these y values here, you're going to understand that. So you see, you went from 16 to 32, so you're stretching. Here, you went from 16 to 8, so you're shrinking. So it kind of makes sense that way, right? So you went from 16 to 8, you're shrinking the y values, correct? If you went from 9 to 4.5, you're shrinking the y value. You went from 4, so you took your y value parent function, you multiply by 1/2, so you're shrinking it. So you're shrinking all of these y values. So this y value of that was 9 became 4.5, and I drew 4.5 a little. I should have done a little bit higher, but that's what's happening. You're shrinking your y values. Okay, so it's right here, isn't it? All right, so I went from, I forget which one I'm looking at now. I'm so sorry. So I went from 9 to a y value of 4.5, and I don't think I drew it. So 4.5 was right here. Yeah, I didn't draw it, so that's where it was. So you're shrinking your y values. So every y corner of the y on the red graph was obtained from the blue graph by shrinking it, by shrinking those y values. So you went from 16 to 32, that's a stretch. So you see, you multiply by 2. You went from 9 to 18, you're stretching. You're stretching. To go from here to here, you're shrinking. All right, so kind of remember it like that. Just kind of have that table in your mind, and that may help you understand the idea of stretching versus shrinking. Okay? So when you stretch, your y values get bigger from your parent function. When you shrink, your y values get smaller. So you see, you're going from this to this now. You're going from this to this now. All right, so you're shrinking your y values. So hopefully that kind of helps somewhat. All right, so we talked about stretching, vertical shrinking with regards to x squared. All right, now what I'm going to do next is look at the next one, horizontal stretching and shrinking. So let's talk about horizontal stretching and shrinking. That is a little bit harder to understand. All right, so horizontal stretching and shrinking. Okay, horizontal, stretching, and shrinking. Okay, so remember when we talked about um, horizontal, I'm sorry, vertical stretching and shrinking? We said that we were dealing with our function that was being multiplied by c. Notice that c is being multiplied by our function, correct? Okay. All right. So c, we're still going to look at the idea of c, or that factor. C though is going to look like this instead. So you're going to have y equals f times c times x, f of c times x. So y equals f of c times x. So instead of you having c times f of x out here, you're going to find f of c times x. So x is being multiplied by c. It is much harder to understand. All right, so let's look at this in terms of a t-table. So we're going to look at, in this case, we're going to look at the absolute value function. Let's do that one. Okay, so we're going to continue talking about horizontal stretching and shrinking. So that's that second one, horizontal stretching and shrinking. And this is where you're going to have c is being multiplied by the variable. So that's what it's going to look like. All right, so in the previous problem, or in the previous lesson, the previous part, we looked at c that was being multiplied by the function. But this time, the variable is multiplied by c. See that? Here, it was your function being multiplied by c. So when your function is multiplied by c, you have a vertical stretch or shrink. If the variable is being multiplied by c, see where c is inside that parenthesis, so f of c times x, then you're dealing with a horizontal stretching or shrinking. Now, it is hard to understand that idea of vertical stretch or shrink. So we're going to use, and before we go to absolute value function, let's look at this. So we have this shape right here, and some students find this particular graph, it helps them to understand this idea better. So let's go ahead and use this to begin with. Okay, so I'm going to list a table of values. So I'm going to call this function f of x right here. So this will be, the blue will be y equal f of x. Okay, and so I'm going to list the table values that we have here, and here are the table values. So I'm going to go ahead and do that here. So we had x, and so if you look at this, when x is negative 4, what's my y value? My y value is 4, right? So when x was negative 4, y equals f of x was 4, okay? When x is negative 2, what's my y value? Well, my y value is 0. So when x is negative 2, my y value is 0. Okay? And also I could have done this when x was negative 1. Negative 1, what's my y value? My y value is 1, right? But I'm going to just go ahead and leave these right here for right now because there's a reason for that. So I'm not going to put negative 1 in there. When x is 0, what's my y value? My y value is 2. Okay, so when x is 0, my y value is 2. Then I'm going to go to the next, see these are segments. I'm just going to go to those endpoints. The endpoints here, the endpoints here, the endpoints here. When x is 2, what's that y value? That y value is 0. When x is 4, what's my y value? My y value is 4. Okay, now what I want to do is this now. So I want to graph y equals g of x. So this time we're going to graph g of x. And g of x this time is this. F of 2 times x. So remember we're trying to focus on c, right? C times x. So what's c in this case? C is what? 2. All right? So what does a factor of 2, what does a factor of 2 do to the graph of this? That's the question. So this graph right here. All right? Okay, so what I want to do now is this. So if I take, and listen carefully to this, okay? So if I take, all right, so if I take this, I'm going to go back and do this right here. So I have x, and then I have f of 2x, which is g of x, right? Okay, so if I take x to be, let's say, negative 2, all right, if x is negative 2, then this becomes f of what? 2 times negative 2, which is negative 4. Y'all agree? You agree with that, right? And f of negative 4, so here's f of x. What's f of negative 4? So if x is negative 4, what's f of negative 4? 4. So when x is negative 2, what is the y value for g of x? The y value is 4. All right, so I get 4. If x is, let's say, negative 1, negative 1. If x is negative 1, the y value, let me go ahead, I guess I should have put it here. So when x is negative 1, what was the y value? The y value is 1, right? Okay. So if x is negative 1, then this becomes f of what? 2 times negative 1, which is negative 2. And what's f of negative 2? Well, f of negative 2 is what? 0. Okay? If x is, let's say, 0, then this becomes f of 2 times 0. And what's f of 2 times 0? That's 0. And what's f of 0? 2. If x, let's say, is 1, if x is 1, I get f of 2 times 1 is 2, so that becomes f of 2. So therefore, g of x is equal to f of 2 is what? 0. And if x is 2, I get f of 2 times 2, which is 4. And f of 4 is 4. So I really didn't need this at all. All right, so here's the point now. So I'm going to plot these points, okay? So I'm plotting those points. So I'm going to do that with a red graph. So I'm plotting the point negative 2, 4. So negative 2, 4 is this, okay? Then I'm plotting the next point, which is negative 1, 0. Negative 1, 0, which is here. All right, so then this becomes this, okay? Then I'm plotting the point 0, 2, which is here. So I get this. And then 1, 0, which is here. Okay. And then 2, 4, which is here. All right. So this right here is f of, g of x, which equals f of 2 times x. So if c is greater than 1, and remember, you're dealing with a horizontal stretching, horizontal shrinking. So what's happening is you're taking the blue graph and you are making it look smaller, right? See how it looks smaller? So instead of this shape right here, you have this new shape which looks thinner, it looks smaller. Okay? So you have basically this horizontal shrinking. So you're shrinking f of x. So f of 2x takes f of x and shrinks it. So it shrinks it, and notice that you're shrinking it by a factor of a half. You may say, well, that's 2. Yeah, but look, you're taking this distance here and halving it, taking that in half. All right, so you're taking this distance here and then taking half of that. So whenever you have a f of c times x, then c is going to be either a horizontal shrink or a horizontal stretch. So you're either going to make it look smaller or look bigger. Okay? So let's go ahead and look at this, and then we'll come back and summarize it. All right, so here's the next one I want to look at. Okay, so now what we want to do is look at this. So what if we had, and I'm going to do the same table right here. What if we have f of 1/2 x? All right, so we know what happens when we have f of 2x, where c is 2. But what happens if it's not 2 anymore, but 1/2? All right, so let's see what happens there. So here's what I'm going to do this. So you got to listen carefully to this. So I'm going to let x be -8. Okay, I'm going to let x be -8, and there's a reason I'm choosing that. You're going to see in a little while. So if x is -8, okay, I have y equals h of x, which equals up here, which is going to equal this. Okay, 1/2 x. So if x is -8, then this becomes h of -8, which is f of, and what's 1/2 of -8? 1/2 of -8 is -4. Okay? And then if I go back to my table I had earlier, this one here, what is f of -4? Well, f of -4 was what? 4, right? So when x is -8, my y value is 4. Okay, so I'm going to plot that point. I'm going to plot the point 8, -8, 4. So I'm going to plot the point -8, 4. So it looks like this. So -8, 4. Okay. Then next one I'm going to use is this. All right, so listen carefully. So I'm going to use -4. If x is -4, then I want to find h of -4. Well, h of -4 becomes the same as f of, what's 1/2 of -4? Well, 1/2 of -4 is -2. So now I'm going to go to my table, and I'm going to see what f of -2 is. Well, f of -2 is 0. So I'm going to plot the point -4, 0. And so -4, 0 becomes this, -4, 0, right here. All right, so then I'm going to draw that line, that segment, and I get this, right here. Okay, so that's one part. So remember, I'm taking f of x, which is the blue graph, right? And I'm transforming it. So I want to know what happens to the blue graph when I want to graph f of 1/2 x instead. All right, so see what's happening? So see how the blue graph, you're stretching it horizontally like this? All right, you're stretching it horizontally. Okay? All right, so we can continue with this discussion. So let's look at the next one then. Let's say we wanted to look at x being, let's say 0. Then I want to find h of 0. H of 0, well, h of 0 is the same as f of, what's 1/2 times 0? It's 0. So let's find f of 0. So f of 0 is 2. So f of 0 is 2. So now I'm going to plot the point 0, 2. So 0, 2 is this, right here. Oops, right here. So then I get this. Okay? Then let's look at x being 4. So when x is 4, I want to find h of 4. Well, h of 4, so this becomes f of 1/2 of 4 is 2. So it becomes f of 2. And f of 2 from our table, f of 2, remember, is 0. So now I'm going to plot the point 4, 0. So 4, 0 is here, right here. Okay, so I get this. Right, and then finally, if x is 8, if x is 8, I get h of 8, which is f of 1/2 of 8 is 4, and f of 4 is, f of 4 is 4. All right, so I'm going to plot the point 8, 4. So 8, 4 is here. So what you notice is this. So remember, this is y equals f of 1/2 x. Okay, so the green graph is f of 1/2 x. So the blue is f of x. See the blue right here? Okay? So if I take x, multiply by a number greater than 1, it shrinks it. So I have a horizontal shrink, a horizontal compression. So it compresses the blue graph, okay, towards the y-axis. If C is less than 1, still positive. Remember, we're only dealing with positive C's. So if C is less than 1, then I have a horizontal stretch. So it makes it look bigger. So you're changing the shape into something that looks bigger. Okay? So we have a horizontal stretch. All right, now let's go ahead and write this down, and then there's something else we need to talk about. Okay, so when we talked about horizontal stretching and shrinking, just like in vertical, we're looking at where C is positive. Okay, so where C is positive. All right. Now, remember, if C is negative, that has to do with a reflection about the y-axis. If C is negative in this case, but we're only looking at positive because we just want to talk about stretching and shrinking without reflections. Okay, so if C is greater than 1, so if C is greater than 1, all right, remember, if C is greater than 1, we had a horizontal, so we went from the blue graph to the red graph, so we had a horizontal shrink, okay, a horizontal shrink. So if C is greater than 1, then we have a horizontal shrink. Okay, or compression, sometimes called a compression. Okay, so listen to this. So when C is greater than 1, then so if C is greater than 1 in the function, y equal f of C of x, C times x, a horizontal shrinking of y equal f of x will occur. Okay, so we go back and it kind of makes sense. So here is our blue graph, f of x. C here was 2, so greater than 1. So we had a horizontal shrink. Okay, horizontal shrink. So we had a horizontal compression. Okay, now if C is less than 1, which is this case here, but still positive, okay, then we have a horizontal stretch. Okay, a horizontal stretch. Okay, now, so we're going to say this. When C is between 1 and 0, so C is less than 1, still positive, a horizontal stretch of the graph of y equal f of x will occur. All right, so basically what that's saying is this. So this is my blue graph, and I want to graph if C is less than 1 but still positive, the blue graph, I'm going to stretch it horizontally. So you're pulling it away from the y-axis. See, here's my y-axis. You're taking that blue graph and you're pulling it away from it. All right, so the shape changes, so it's a different shape. It still has how the segments look. Okay, so like this, it still does that, but it's a different shape. You're either compressing it or stretching it. Okay. All right. Now, There's some other things we need to talk about this, but I'm going to do this in the next part of the lesson. So let's just quickly do a review with these two parts. So it's a couple of takeaways I need for you to get from this, and that's this. So we talked about vertical stretch compression. We talked about horizontal stretch compression. A vertical stretch occurs. A vertical stretch occurs if you take your function and C is being multiplied by. See where C is on the outside? Okay. A vertical horizontal shrink or stretch occurs if you're multiplying C by X. So where instead of C being on the outside, it's inside the parentheses and it's C times X. Right? And so going back to the vertical stretch or compression, if C is greater than 1, so if C is greater than 1, it is vertically stretched. If C is less than 1, still positive, it's vertically compressed. If you're talking about horizontal, if C is greater than 1, it's a horizontal shrink. So meaning this, and if you can have this in your mind, it kind of helps. So here's the function f of x. I want to find f of 2x, so I'm stretching it. I'm horizontally shrinking it. Okay, over here, I'm horizontally stretching it. All right, so if C is less than 1 but still positive, you have a horizontal stretch. All right, so that is going to be the end of this lesson. It was a pretty long lesson. It is not an easy thing to understand. There's another graph I wanted to use with this, an absolute value one, but it was just too long of a lesson. So I'm going to stop here, and then there are a couple more things that we need to talk about though. But I'm going to put that in a different lesson. So this is going to end this lesson.